My name is Pavel. Today I want to talk to you about how you, one approach how you can understand C++ coroutines. By example, how you can think about them, how can you obtain intuition of how they work, and let's see what we'll see today. Well, as you may know, in C++20 we have coroutines, but we have no ready user-facing support for coroutines. So one way you can use coroutines more or less painlessly is to use CppCoro by Lewis Baker. And well, that's it. Thanks for coming. And yeah, I did not share sound, so you should imagine music going there. And on a more serious note, let's see what we'll discuss today. We'll have kind of like 3 iterations. Iteration 0 will learn how to write coroutines. By example, kind of my first coroutine. We'll see what is a C++ coroutine and a bit demystify, try to demystify the compiler magic that handles the code that you write. On iteration 2, on iteration 1, sorry, zero-based indexing, we'll learn how to await tasks and make awaitables. On iteration 2, we'll learn how to get a result from tasks, from asynchronous tasks. We'll examine and try to make our code thread safe. And finally, we'll try to analyze the approach that I'm going to present to you and see what we can do with it. Can we make it better, or is it good enough? Okay, iteration 0, my first coroutine. You can see at the top of the slide a function that has only one statement, coreturn, and it is actually a coroutine. Any function that contains one of 3 keywords, coreturn, coawait, coyield, is a coroutine and is handled in a special way. So let's recap how we get here. Here is a little taxonomy of routines. So routine or a program, it branches off to subroutine and coroutine. Coroutine is a sibling of subroutine. And in C++, we got stackless coroutine as compared to stackful coroutine that are also called sometimes fibers. As you know, C++ borrowed a lot of things from Simula, and Simula, among other things, introduced coroutines some 60 years ago. Here it is. I was told that Simula 1, some years before, had coroutines in some form, so it's even more, before the Simula 67 that we had some kind of coroutines, some form of coroutines. So let's see what the compiler does with the code that we write. Here's a coroutine, and the standard says that it is transformed as if the function of the body is replaced by this pseudocode. And you can see it as following. So we have our coroutine. We have initial suspend point, final suspend point. When we call our coroutine, we get to the initial suspend point. At this point, we can suspend our coroutine or continue the execution of the body. And by the time we get to final suspend point, again, we can just finish coroutine, or again, we can suspend the coroutine, and we will end up with the coroutine in the suspended state. So we'll try in this talk to a bit uncover this magic of the C++ backend, C++ compiler backend that handles all this. And so the compiler does transformation to the code that we write. So on the left, you can see the code that I wrote, and on the right will be a notion of a code that the compiler might transform your code into. So this is not literally what compiler does, but I wanted to illustrate the idea that stands behind this transformation. So from that simple code, we get this coroutine frame contains promise type that we have to implement ourselves and some other state stuff. In this case, it's a flag that tells that our coroutine has been initialized successfully, initial await resume code. And we have a state flag that tells to which suspend point we have to return, and from which suspend point we have to resume the execution of the coroutine. So by the way, coroutines are just state machines. So the compiler just cuts the code that you write into a state machine, and basically this coroutine frame contains all the ingredients you need to operate this as a state machine, hence the state variable. So the next thing the compiler does is allocating, in general, the coroutine frame with operator new. Yes, in general, coroutines require allocation of memory, but there are situations where the compiler can deduce that allocation is not needed, and it uses stack instead to hold all the state stuff. The next thing is we want to acquire the object that we will eventually return from the coroutine. So we do this by calling getReturnObject from the promise object that lives inside the coroutine frame. And remember that object, basically store this object into a variable on the stack. The next is calling the body of this coroutine function, basically using the operator function call. And the last step, when the control returns to this scope, we return the object that we acquired from the promise by calling getReturnObject. So the next step is to fill the body of the function by using that mentioned transformation from the standard. And basically we add to the function call operator a try catch block and some additional stuff. Here we have call waits, but for now we'll treat it as magic. And the next thing that we have is coroutine statement. Coroutine statement is transformed into this construction. Instead of that statement, we just call the return value member function from promise, and then go to final suspend. If we had an exception at any point, for example, we could have an exception from initial suspend function call, or from return value function call, or from other code that we could have in the body of the function of our coroutine function. If an exception happens, the catch clause catches all the exceptions. If we have if our coroutine failed to even initialize, we have our initial await resume called flag equal to false, and we just rethrow the exception. Otherwise, we assume that our coroutine have initialized, and we call unhandled exception member function on the promise object. Unhandled exception function can handle the exception, for example, save exception pointer, or otherwise handles exception. This is the responsibility of the user, or basically us. And let's see what operations we, or what interface we need to implement for our coroutine to work. In sequence, we need to implement promise type that is located inside our task type. Our task type with the type of asynchronous result that we can get, that gets ready at some point in time in the future, or it may get ready immediately, we don't know, hence it's synchronous. The next is get return object. This is needed to obtain object that will be eventually returned from the coroutine call. The next is initial suspend, which tells us how we want our coroutine to behave at the initial suspend point. The next is return value, which is called when we have co-return statement, which receives the value that we wanted to co-return. The next is unhandled exception, called on the promise in case we had an exception. And the last one is final suspend, which tells us how we want the coroutine to behave at the final suspend point. So here is our task type. You can see that we have a distinct promise type that we'll define later. We have an alias promise type with name promise underscore type, which is equal to specialized promise type. We have to have this exact name promise underscore type to communicate which promise type we want the C++ compiler backend to use. Next is default constructor, which basically doesn't do anything really. The next is private constructor for our convenience. We'll use it later. Next we have promise pointer, or like the notion of promise pointer, which is just like array II style container that holds pointer to promise and destroys properly the coroutine when the pointer, when the smart pointer itself is destroyed. So we initialize it with null_ter to indicate that we don't hold any live pointers at the time of initialization. And the last thing that we have is friend declaration for our struct promise type. This is needed so our promise type can get to private members of our task type. I hope it's self-explanatory so far. So let's see at our promise type. It has the five mandatory functions that we need to implement. And we have here some convenient stuff that we implemented, that I implemented for my convenience. So we have the only field result. This is a variant. The variants are monostate to indicate that nothing is stored, no value or no exception is stored. And otherwise we can store a type, a value of type that our task is associated with, or we can store exception pointer. The next is get return object, which just uses the constructor that we defined in the task, the private constructor. We pass pointer to this object as an argument. So we this way we establish connection between the task itself and the promise. This is used in the when we call coroutine, our coroutine function in this way. When we get to this point where we try to obtain return object, the object that will be returned from the coroutine, get return object is called. We return an instance of our task that is saved in the return object variable, and eventually that object or our task will be returned from the coroutine. So yeah, here we call the get return object. The returned object is stored in the return object variable, and eventually it will be returned from the coroutine call. The instance, the return object, the instance that is connected to this promise object. So the next is initial suspend and final suspend. We decide here that we want a so-called eager task that starts to execute the body when the coroutine is called. So when we call the coroutine, at the initial suspend point, we do not suspend the coroutine. We continue to execute the body of our coroutine and only suspend at the final suspend point, because we want to save the state of the coroutine. For example, if an exception occurred, we want to be able to get that exception from within the coroutine state. So in the final suspend point, we suspend the coroutine. The next is return value, another mandatory function, member function that we need to implement. This is called when we co-return, for example, a value. In this case, when internal operator function call is called, and we get to transform co-return statement, return value is called, and that way we can store the value that the programmer wanted to return from the coroutine. And we have to specify no except specification. You can just ignore it. I included it for completeness. And the implementation is also rather simple. We just place the value that we got as a parameter, as an argument, and store it in our variant result field. The next one is unhandled exception. Unhandled exception is called in the catch clause in case we had an exception in the body of the coroutine or during the initialization of the coroutine. Again, we need to specify no except specification, because the standard doesn't say if the exception pointer is does not or does throw exceptions during copying. We have to have this specification, unfortunately, but you can ignore it. And implementation is very similar to return value member functions. Here we just in place for the index 2 for our exception pointer, the exception pointer that we get from current exception call, and store it in our variant result field. The next one is for our convenience. It is not mandatory. Here we just can check that we have a ready result. So in this case, it's kind of either we have an actual value or we have an exception. If we have an exception, we also consider that this promise and the task that is connected to it is ready. And we have get result, again, not mandatory. This is for our convenience, and the implementation just checks if the actual result have an exception. The index equals 2, we rethrow that exception that we get from the result variant. Otherwise, we just move the result value out of this member call. And so I hope it makes a bit of sense. We have 5 mandatory member functions that we have to implement to in order for compiler backend to be able to handle the coroutine that we write, and we have 2 convenience member functions, non-mandatory for convenience, and we have variant result field. So let's next we can write a code like this. We wrote a coroutine that when we call it prints something to the console and then immediately returns a value. We can call coroutine like that. We save the an object, task object that we get from the coroutine in the task variable, and when we run it, we get output like this. We have a question. Is there anything similar to return value optimization when getting a value from a core return expression, though through promise return value and into the variant? Well, this is a good question. This is not covered in this talk. I recommend you to catch my other talk that will be tomorrow. I will answer a similar question in that talk, but here you can do that, of course, but in this presentation we don't do that. So basically we move the value that we want to return all the way from the return statement outside of the task object that we got from running the coroutine. Okay, I hope I at least partly answered that question. So here we have a coroutine, we have a task that our coroutine returns a task that is instantiated with void type, so it doesn't return anything, and co-return also doesn't have a value to return. And in this case, we have to have a specialization for promise. For void, probably I should have explicitly specialize the promise here in the code below. But the only difference is that instead of return value, we need to implement return void that doesn't accept parameters and also doesn't return any parameters. So this is the only difference when we want to co-return a value, or we just co-return nothing. Yeah, and when the compiler transforms the code, instead of calling return value, it calls return void on the promise object. And yeah, so let's recap. In order for our coroutine to work, we need to implement promise type in order to communicate to the compiler backend what we want the behavior of the coroutine to be. And we want to implement the 5, in this case, mandatory member functions. And yeah, we are done with the first part, with iteration 0. Let's get to iteration 1, in which we will learn how to await tasks in the coroutines. In this case, we have another coroutine that calls our first coroutine foo. We'll get a task from the coroutine foo in the variable result, and we can't just use that object. We, in this case, have to call wait on that result. And only after we call wait that result, we can be sure that the task that we call wait on basically is ready. And we, after that, can use the actual value, the result value that we got from that coroutine, from the full coroutine. It's time to uncover call wait magic a little bit. So expression call wait at the top is transformed into a construction like this at the bottom. We have to somehow get an awaitable object from that expression, from the call wait expression. Then we check if that awaitable signals that the result is ready. If the result is not ready, we call await suspend to that awaitable, pass coroutine handle of this coroutine into await suspend in order to prepare for suspension of this of the current coroutine. And in that case, the coroutine suspends. Otherwise, or when the result is ready, the coroutine is resumed. We get to the bottom part. Await resume is called, which just is used to extract the value, the result that is now ready for that expression, call wait expression. So again, here is on the left what we wrote. On the right is what the compiler transforms it to, not literally, but it illustrates the idea behind it. And let's see what happens. So finally, we get to the operator function call that is implemented by the compiler inside coroutine frame. And here we have clearly a state machine. So we check the state when the coroutine is called first time, or it is resumed. We check the current state value, and we basically jump to the corresponding location that we need to resume our coroutine from. So we get here, we check our state. When we call our coroutine the first time, the state is initialized to 0. So we just get to case 0 and just don't bother with all the other cases and just skip it altogether. The next line, so notice, so this is the beginning of the call when we call a coroutine, and when we get to the operator function call that is called immediately after coroutine is initialized. And now we get to the initial suspend point. Here, this that you can see above, the code is transformed into a construction like this that you can see below. So again, we from initial suspend, from the result of the initial suspend call, we need to get awaitable object somehow, and we have a variable awaitable 0 that we store this awaitable object in. Next, we check if the result corresponding to that awaitable is ready. If it is not ready, we call await suspend, passing this coroutine handle and return, basically return the control outside. Sometime later, we can resume this coroutine, and it will get to this label, initial resume. We'll call await resume to get the result of that awaitable. And so between suspension, basically returning the control, and resumption, when the control gets back here, we have to store that awaitable object somewhere, because we eventually want to call await resume on that object. And so to do that, the compiler basically adds a field to the coroutine frame. In this case, this is optional, because we might not get to this point and we want to properly this object to be properly destructed. So it's either empty optional or some value contained in the optional, and this guarantees that the object will be destroyed gracefully. And so this also guarantees that this object will be alive between suspension and resumption of the coroutine. And so in this kind of pseudocode, we emplace that resulting awaitable in the field of the coroutine frame. And in our case, the awaitable is suspend never, which always tells that the result is always ready, and there is no need to call await suspend, and also await resume returns nothing, and the implementation is also empty. So in this case, since the result is ready, when we ask for it, we just skip the suspension and get straight to initial resume label and call await resume to get the value that might have been in the awaitable object. The next is our body of our coroutine. So the first line is getting the task from coroutine full. The next line is awaiting on that result. And these two lines are transformed into this construction. So when we get here, we call the coroutine as usual. We get the result, which is a task. We set the state to 2 to reflect that we get to this point. We place again an awaitable. In this case, it looks like this. It uses so-called symmetric control transfer. So the await suspend returns a coroutine handle and receives the coroutine handle. And the compiler basically suspends the current coroutine and immediately resumes the coroutine that we get from await suspend call. So this core handle refers to the current coroutine that is to be suspended, and the core variable holds the coroutine handle of the coroutine that is to be resumed immediately after this current coroutine is suspended, and the code the pseudocode that illustrates this looks like this. And so when we get here, we again emplace awaitable in the coroutine frame. We suspend the current coroutine and resume the coroutine that we get from await suspend in case the result associated with awaitable is not ready. At some point, this coroutine that is suspended is resumed. In that case, we get straight to label resume 2. We call await resume, and the execution continues. Otherwise, if the result associated with awaitable is ready, we skip all the shenanigans with suspending and resumption of the coroutines. We get to resume 2 label, and again we call await resume to get the result out of the awaitable. Again, since we want the awaitable to live between suspension and resumption, we put it in the coroutine frame. like this. The next and the last line in our body is Coroutine some expression. So this is transformed into a construction like this. We have basically the awaitable await resume line from the previous slide, and the co-return statement is transformed into promise return value call and go to final suspend label. In case again I'm running ahead of myself. So in case everything goes smooth, we just get to straight to final suspend label, but we can encounter an exception, and in that case we get to catch clause. We check if the coroutine was actually initialized successfully. If that's not the case, we just rethrow the exception. Otherwise, if the coroutine was at least initialized successfully and the exception was originated from, for example, the body of the coroutine, we call unhandled exception call on the promise object, which is supposed to handle the exception, for example, save the exception pointer. And anyway, we somehow get to this part, the final suspend part. Here we call wait on the final suspend on the result of the final suspend call on the promise object, and this is transformed into a construction like this. Here we get final awaitable. When we get here from final suspend call, in our case, the final awaitable is suspend always, which is never ready and does nothing actually when the coroutine is suspended. So the await suspend is implementation is empty, and we basically check that the result is indeed not ready, suspend the coroutine, and return the control. And in this case, we basically never get to delete this because we always suspend the coroutine at the final suspend point, and we never basically finish the coroutine, but we never implicitly release all the resources. So we now want to await for a task in order to get a result that task is associated with. And the easiest way to do this is to implement co-await operator in the task itself. So this is how the co-await operator looks like. We have an awaitable type inside of the co-await operator, and we just return an instance of that awaitable type, initializing it with a reference to this promise, to the promise that this coroutine is associated with. So here is the implementation of the awaitable type. We ask when we are asked if the result is ready, we just ask the promise if the result is ready at this point, and just return that result readiness status outside. When the result is not ready, the coroutine is suspended. In our case, we use so-called symmetric control transfer. We get as an argument a coroutine handle that is to be suspended, and set it as a continuation of this coroutine. So again, the current running coroutine is to be suspended, and we set a coroutine handle of that coroutine as a continuation of the coroutine that is to be resumed. And so this is basically we get a coroutine handle of this coroutine that is associated with the task, and return a coroutine handle from await suspend. Again, so when we co-wait on the task, we have a current coroutine, and we have a coroutine that is associated with the task object. And when we co-wait, when the result is not ready, we suspend the current coroutine and resume the coroutine that is associated with the task object. Using the, in this case, symmetric control transfer. The last member function that we have to implement, by the way, these three functions are mandatory in the sense that we need to implement them in order for the compiler backend to handle call wait expressions. So the last one is just basically returning the result out of the task using the promise that is associated with the task and the coroutine. And we're basically returning an error value reference, so the user can move the result out of this task object. So you already saw that we have to have a continuation field that we use to basically chain coroutines. So when one coroutine is suspended, the other chained coroutine is resumed, and so on. And another thing that we have to change is final suspend. In this case, we can't use suspend always, and we have to roll out our own final waitable. This is needed because we need to, in this case, resume the continuation if we have one. We'll get to that. So the first mandatory function is await ready. We say that the result is always false, so the result is never ready. The next is suspend, in which we basically suspend this coroutine. We prepare to suspend this coroutine, the current coroutine. We check if this current coroutine has a continuation, and if it has, we want to resume that continuation. So basically, when this current coroutine finishes, we want any continuation attached to it, chained to this current coroutine, to resume. So the last one is basically not used because await resume is now called at final suspend point. And we finally can write something like this, and we get from that program output like below. So view, I think we tackled that part. Finally, we can now call wait on tasks, and we can have an intermission with Peter.pool and see what helpful tip he has for us. So when you write promise type, you can write constructors and destructors, and you can, for example, write traces or logs or somehow otherwise put anything that can help you debug or track promise lifetime, because promise lifetime is connected immediately to coroutine frame. In this way, you can kind of accurately track lifetime of the coroutine frame and check if you leak coroutine frame, for example, by not destroying the coroutine at the right time, or maybe you destroy the coroutine frame at the wrong time, and you have dangling references and whatnot. So here's a helpful tip. The next part of this iteration is we want to write some other awaitables. We want to await on other things other than tasks. So in this case, we want to write a sleep awaitable that puts the current thread to sleep. In order to do this, we can implement it like this. Await ready checks if the duration is non-zero. And in that case, it means that the result is not ready and we need to suspend the coroutine. In the await suspend, we get the coroutine handle of the coroutine that is to be suspended. Basically, it is suspended at the point of calling await suspend. And we can put the current thread to sleep. And after the thread wakes up, we can resume the coroutine that was suspended, effectively putting the thread to sleep using coroutines. And so await resume does nothing, and that's the implementation, and we can use it like this. So we can, when we run this program, we get output, of course, like this. We get the first part, and then after 1 second, we get the second part. And yeah, Rick says that, well, that just sounds like putting a thread to sleep with extra steps, and he's right. Let's do something else. Let's implement async read file, like asynchronous for real, with an extra workers thread and whatnot. So here's the implementation. In the constructor, we basically just initialize the path field. In await ready, we say that the result is not ready because we need to launch a worker thread and read the file and whatnot, and so we don't believe that the result will be ready soon. So the next is await suspend that we get to later, and in await resume, with which we return the resulting value, we just move the result that is stored in this async read file type as a field. So here's how await suspend looks like. We define what we want to do inside the Lambda. We capture this pointer and coroutine handle. We fire a stream. We read from that stream into the result. And after that, we resume the coroutine. So yeah, and finally we launch a worker thread, giving it this lambda to run. And in this case, I use detach, and please do not use detach like this in your production code. Please do not do this. This is for illustration purposes only. And so we can use that awaitable like this. We can write a coroutine read file that co-awaits on an instance of async read file. We pass a path to a file, in this case main CPP, and then we co-await on that async read file instance. We get the result, and we return size of that result from that coroutine. We can run that program. Oops, sorry. And we get results like this. So we can see the start of the coroutine execution, but we don't see the end of the coroutine execution. Why does it happen like that? So thread A, for example, our main thread, we have this coroutine running, we get to inside the coroutine, we call it, we create a worker thread by call-waiting on async read file. Our worker thread eventually will resume this coroutine. So this coroutine that is started on thread A will eventually be resumed on thread B in this case. And after starting the worker thread, we suspend this coroutine, we return the control outside. And basically, if we are in main finishes, after finishing main, exit is called and the program finishes. So we have a question, I think. Okay, let me finish this thought and I'll get to the question. And so when we call exit, the program finishes and we basically pull the rack out of the worker thread, not giving it a chance to finish. So, okay, yes, iteration 2, in which we learn how to get results for real and make it thread safe-ish. So the result is the actual result value is in the promise and specifically in the result field that lives inside the promise. So in this case, when we have a coroutine that is executed on a different thread, for example, we one variant is to somehow understand that the result is ready, that the coroutine, for example, has finished on the other thread, and we can safely get the result. Outside of coroutine, we should be able to get it in a synchronous manner. So in this case, we can use std_future to use as a synchronization primitive. We can add a continuation to the coroutine that we are currently want the result from. And when we execute it, we start the coroutine. The coroutine starts execution on different thread, for example, hypothetically. Then we add a continuation. The promise in the continuation is connected to the result future that we can wait on. Then we get to the waiting part. When we call get on the future, possibly this thread blocks because we haven't got result yet. Eventually, the coroutine finishes. It executes a continuation. In the continuation, we set the result. We set value on the promise that signals to the future that the result is ready, and we can continue the execution on the initial thread. So this I will skip because we have no time. This is basically all the machinery needed to organize that synchronous wait. And eventually we can write a code like this. We can call the coroutine, get the task out of the coroutine call. We don't know if the result associated with this task is ready or not. So we call sync_wait, passing the task into this sync_wait that guarantees us that no matter how the coroutine is executed, we'll always get result, maybe just in a synchronous instead of a asynchronous way. And so we can write a program like this, and finally it will work as expected, and we'll get the results out of the coroutine in a synchronous way using sync_wait. So there is one drawback in that scheme is that we want to have all of that thread safe. And what do we need to make that thread safe? Of course, to sprinkle some atomics on the task and promise implementation. So I'm sorry, I have 1 minute left. I will skim through the implementation. So we have here states, started, attached, continuation, and finished, that we can assign to an atomic variable. We have a final awaitable in the final suspend, in which we exchange the state to finished, and then we check if the state was attached continuation. That means that we had continuation, we resume the continuation, and in isReady, we instead of checking the variant, we check the state, and if the state is finished, means that the value is ready. And here in the task co-wait operator, we need to compare and exchange states. If the state was started, that means that the result is not ready and the coroutine is suspended. Otherwise, the state was finished and the result is ready. We can get the result from the promise, from the task, and the coroutine is not suspended. And so finally, we can write code like this, in which case we sync wait for the result of read file coroutine. And finally, we get the full output, full expected output of this program. Only maybe we get this presentation of the output because the output stream is not synchronized. And finally, we finished the iteration 2, and we have just a couple of slides more. I'm sorry to go over time. I have a couple of minutes more. So in this case, with all that thread safety, we still can get into trouble just by throwing, unfortunately, an exception before we can get result from task. And in this case, the task is destroyed, all the resources are freed, and basically we pull the rug from under the thread, possible thread that executes the coroutine. So we have dangling references and all that beauty, and this is basically a shot in the foot. So we shouldn't do this, and in order not to do this and to use it safely, you can, one possibility is to use CppCore by Lewis Baker. The star there is because, for example, CppCore is written against experimental implementation, and I don't know any library that is not written against production implementation, not experimental. That's why I recommend CppCore, but with the asterisks. And in fact, what we need to do is just take code from iteration 1. Instead of not suspending initially, we want to suspend always initially. That changes the behavior in the way that when we call a coroutine, the execution of the body does not start. We can safely, for example, throw exceptions. Everything will destruct beautifully, no dangling references, pointers, and all that beauty. And the execution of the coroutine, of the body of the coroutine, starts only when we await on the coroutine. And so good news is that probably we'll have an implementation of the like called std-lazy, proposed by a paper by Casey Carter, P2506. It is lightweight. It starts execution when awaited on, for example, when co-awaited in a coroutine or when awaited synchronously. And I advise to watch Lewis Baker's talk on asynchronous, basically asynchronous, he calls it structured concurrency. It touches on asynchronous processes like that you can write using coroutines. And I have another talk. If you're watching a recording, just Google it. And sorry for taking extra time. Thanks for listening. Thanks to Lewis Becker for feedback. I still owe him beer. And that's it. I think we have no time for questions. And yeah, we'll see probably in Gather Town. Bye.